The observation of a standard vessel of water presents an image of absolute tranquility and chemical passivity, serving as a transparent medium that facilitates the most fundamental biological requirements of terrestrial life. Water is frequently perceived as a benign and neutralizing force, yet a rigorous atomic analysis reveals that this liquid is a sophisticated containment system for a primordial and high-energy chemical reaction. 2/3 of the atoms within a common glass of water are composed of element 1, hydrogen, which is recognized as the most volatile, energetic, and reactive gas in the known universe. In its diatomic gaseous form, hydrogen possesses a staggering energy density and a profound chemical affinity for oxygen, making it the primary constituent of high-velocity combustion and rocket propulsion. If the chemical bonds between the hydrogen and oxygen atoms within a standard household glass were instantaneously severed through electrolysis, and the resulting gases were subjected to an ignition source, the resulting release of thermal and kinetic energy would be sufficient to structurally dismantle the immediate environment. The reality of terrestrial existence is that the very substance required for biological hydration is a tamed explosion, where the latent fury of the most flammable element in existence has been locked into a stable molecular geometry to create a cradle for life. The significance of hydrogen extends far beyond its role in hydration, as it serves as the foundational building block for the entire periodic table and the structural architecture of the cosmos. Approximately 90% of all atoms in the observable universe are hydrogen atoms, representing the primary legacy of the initial moments of the Big Bang. This element is not merely a component of the environment, it is the environment itself. The human biological form is an intricate manifestation of this primordial matter, with 2/3 of the atoms in a human body consisting of hydrogen. These protons were forged 13.8 billion years ago, long before the formation of the first stars or the development of the solar system. Every individual is composed of atomic survivors that have traversed the vast chronological distances of deep time to assemble into a living, thinking organism. The simplicity of the hydrogen atom, a single proton orbited by a single electron, belies its profound capability to drive the nuclear furnaces of the stars and dictate the structural integrity of the genetic code. The transition of hydrogen from a chaotic, high-energy gas into a stable constituent of water is one of the most significant thermodynamic events in planetary history. In its gaseous state, hydrogen is exceptionally light, possessing a molecular weight so low that it easily escapes the gravitational pull of rocky planets, which explains its relative scarcity in the Earth's atmosphere compared to its abundance in the interstellar medium. However, when hydrogen enters a covalent bond with oxygen, it undergoes a transformation that lowers its potential energy, resulting in the release of heat and the formation of a liquid that remains stable across a wide range of temperatures. This molecular marriage is what allows the most aggressive fuel in the universe to flow harmlessly through the human circulatory system. The dual nature of hydrogen, as both a harbinger of catastrophic energy release and a fundamental requirement for biological stability, positions it as the most critical variable in the search for extraterrestrial habitability and the development of future energy systems. The exploration of this element requires an objective understanding of the forces that govern the subatomic world. Hydrogen is the only element that exists without a neutron in its most common isotopic form, protium, making it the purest expression of baryonic matter. Its simplicity allows it to function as a universal solvent, a structural anchor for organic molecules, and a high-density energy carrier. As global technology moves toward a post-carbon economy, the mastery of the hydrogen atom represents the ultimate frontier of engineering. We are currently developing the capability to reverse the bonds formed billions of years ago, liberating hydrogen to power our transport and heat our cities, with the only byproduct being the return of the water from which it was extracted. This cyclical relationship with element 1, highlights the possibility of a sustainable future mediated by the very element that initiated the history of the universe. To ensure the continued dissemination of these high-density scientific narratives and to maintain the reach of these educational explorations against the entropic nature of digital algorithms, the participation of the audience remains a vital component. Supporting the channel by subscribing, activating the notification bell, and contributing to the technical discussion in the comments section assists in the preservation of the analytical reach of this content. By providing a comment with the specific term __, quote _1__, the observer indicates their engagement with the fundamental building blocks of this narrative, helping to prioritize the visibility of scientific discourse in an increasingly crowded media landscape. This interaction serves as a structural reinforcement for the channel, allowing for the deep investigation of materials that define our technological and biological reality. The chemical behavior of hydrogen is governed by its desire to achieve a stable electronic configuration, a process that drives the formation of the complex hydrocarbons and proteins that constitute living tissue. Because hydrogen possesses only one electron in its 1s orbital, it is constantly seeking a partner to fill its valence shell, creating the quote 2 that allow water to possess its unique properties of surface tension and high specific heat. These bonds are also responsible for the quote 3 structure of the DNA double helix, providing a level of stability that is strong enough to preserve genetic information, yet flexible enough to be unzipped during cellular replication. Hydrogen is the molecular mediator that allows for the complexity of life to emerge from the simplicity of the atom. It is a material that has spent billions of years in the vacuum of space, only to find its ultimate utility in the microscopic machinery of a cell. The energy potential of hydrogen is most clearly observed in the process of nuclear fusion, which occurs in the cores of stars like the Sun. Under extreme gravitational pressure and temperatures exceeding 15 million degrees Celsius, hydrogen nuclei are forced to overcome their natural electromagnetic repulsion and fuse into helium. This process results in a minute loss of mass that is converted into a staggering amount of energy, according to Einstein's equation E equals mc squared. E equals mc squared. This is the quote 4 that humanity is currently attempting to replicate on Earth through projects like the International Thermonuclear Experimental Reactor, ITER. The objective is to harness the same power that illuminates the galaxy, providing an inexorable source of energy that is as old as time itself. Hydrogen is the fuel of the stars and the potential salvation of the Earth, serving as the bridge between the origins of the cosmos and the survival of a high-technology civilization. The historical trajectory of our understanding of hydrogen reveals a journey from the observation of quote 5 in the 18th century to the precise manipulation of isotopes in modern physics. We have moved from a species that was unaware of the composition of water to a species that can utilize hydrogen to propel spacecraft across the solar system. The element remains unchanged, yet our ability to interact with it has redefined the limits of human capability. Hydrogen is the silent witness to every chemical reaction in the atmosphere and every metabolic process in the biosphere. It is a material that demands a sophisticated level of respect, as its density and reactivity provide no margin for error in its industrial application. The quote 6 of the water glass is a reminder that the most common substances in our lives are often the ones that possess the most extraordinary physical history. In the contemporary geopolitical landscape, the transition to a hydrogen economy is being driven by the necessity of energy security and the mitigation of environmental degradation. By utilizing renewable energy sources like wind and solar to drive electrolysis, we can create quote 7 effectively storing the energy of the weather in a chemical bond. This allows for the transport of energy across vast distances and the powering of heavy industry without the release of carbon dioxide. Hydrogen is thus the essential carrier for a decarbonized world, a gas that provides the high energy output of fossil fuels without the associated atmospheric cost. The __quote_8_ is becoming the primary solution for the challenges of the 21st century, demonstrating that the simplest structure in the universe is the most versatile tool for our survival. The density of facts surrounding element 1 provides the necessary context for its role as the architect of the universe. It is the primary constituent of the gas giants, the main sequence stars, and the vast nebulae that serve as stellar nurseries. Within the human context, it is the primary constituent of our fluids, our tissues, and our genetic code. We are, in a very literal sense, a complex form of hydrogen that has developed the capacity to analyze its own atomic structure. The relationship between the observer and the element is one of total integration. We cannot study hydrogen without studying ourselves, as we are a direct product of its multi-billion-year journey from the Big Bang to the present. As we look toward the subsequent chapters of this elemental exploration, the focus will shift from the domestic tranquility of a water glass to the chaotic and violent environment of the early universe. We will follow the hydrogen atom through the formation of the first galaxies, the ignition of the first stars, and the eventual development of the chemical complexity that allowed for the existence of rocky planets. Hydrogen is the narrative thread that connects every event in the history of matter, a substance that has remained constant while the universe has grown increasingly complex. It is the beginning of everything. The __quote_9_ of the periodic table, and the material that continues to define the boundaries of our knowledge. The following blocks will reveal the cosmic architecture of element 1 and the historical drama of its discovery, showing how a gas that was once a scientific mystery became the most important asset for a civilization that refuses to be limited by the Earth. Hydrogen remains the __quote_10__ for a reason, and its story is the story of the universe itself. The thermal evolution of the early universe followed a trajectory of rapid expansion and cooling that dictated the initial distribution of baryonic matter, establishing hydrogen as the foundational architect of the cosmos. In the immediate aftermath of the Big Bang, during the first microseconds of existence, the universe consisted of a high-energy plasma of quarks and gluons, a state of matter too energetic for the formation of stable composite particles. As the temperature dropped below critical thresholds, these quarks began to coalesce into hadrons, primarily protons and neutrons. A single proton constitutes the nucleus of a hydrogen atom, meaning that the fundamental components of element 1 were effectively the first stable complex structures to emerge from the primordial fire. By approximately 3 minutes after the initial singularity, the process of Big Bang nucleosynthesis had begun, where the high-density environment allowed for a brief window of nuclear fusion. Protons and neutrons collided to form deuterium, which subsequently fused into helium-4 and trace amounts of lithium. However, as the universe continued its rapid expansion, the density and temperature fell below the levels required for the synthesis of heavier elements, resulting in a primordial chemical composition of approximately 75% hydrogen and 25% helium by mass. This specific ratio remains one of the most significant empirical signatures of the early universe, serving as a permanent record of the conditions present during the first 20 minutes of cosmic time. Following this initial burst of nucleosynthesis, the universe entered a phase known as the recombination era, which occurred roughly 380,000 years later. During this epoch, the expanding cosmos had cooled to approximately 3000 Kelvin, a temperature low enough for protons to capture free electrons and form neutral hydrogen atoms. This event had profound cosmological consequences, as the removal of free electrons allowed photons to travel through space without constant scattering, rendering the universe transparent for the first time. The light released during this transition is still detectable today as the cosmic microwave background radiation, a faint afterglow that provides a high-resolution map of the early distribution of hydrogen. For the subsequent hundreds of millions of years, the universe remained in a state referred to as the Dark Ages, characterized by vast, cooling clouds of neutral hydrogen gas that filled the void between the initial fluctuations of matter. These clouds served as the raw material for the eventual emergence of structure, as the force of gravity began to act upon the subtle variations in gas density, initiating a multi-billion-year process of gravitational collapse. The transition from a dark, featureless universe to a structured cosmos was driven by the gene's instability, a physical phenomenon where the internal pressure of a gas cloud is insufficient to counteract its own gravitational pull. Within the massive molecular clouds of the early universe, regions of higher density began to contract, accelerating as they drew in more surrounding hydrogen. As these clouds collapsed, the gravitational potential energy was converted into thermal energy through the Kelvin-Helmholtz mechanism, causing the centers of these nascent structures to reach incredible temperatures. When the core temperature of a protostellar cloud surpasses the threshold of approximately 10 million Kelvin, the kinetic energy of the hydrogen nuclei becomes sufficient to overcome the Coulomb barrier, the electromagnetic repulsion between positively charged protons. This marks the moment of stellar ignition, where the strong nuclear force takes over, allowing protons to fuse into helium. This first generation of stars, known as population 3 stars, were massive, short-lived entities composed entirely of primordial hydrogen and helium, responsible for the initial reionization of the universe and the synthesis of the first heavy elements. The internal mechanics of a main sequence star, such as the Sun, are predicated on the proton-proton chain reaction, a multi-stage fusion process that serves as the primary energy source for the galaxy. In the solar core, 4 hydrogen nuclei are eventually converted into a single helium-4 nucleus through a sequence of collisions and radioactive decays. This process involves the emission of positrons and neutrinos, as well as the release of high-energy gamma photons. Because the mass of the resulting helium nucleus is slightly less than the sum of the 4 initial protons, this quote 11 is converted into energy according to the principle of mass-energy equivalence, E equals mc2. E equals mc2. This energy migrates from the solar core to the surface over hundreds of thousands of years, eventually radiating into space as the light and heat that sustain the Earth's biosphere. The Sun is currently consuming approximately 600 million tons of hydrogen every second, a rate of consumption that defines its lifespan and the stability of the solar system. Hydrogen is the fuel of the stars, the currency of cosmic energy that allows the universe to counteract the encroaching darkness of entropy. The distribution of hydrogen in the interstellar medium, ISM, provides the primary data source for mapping the structure and evolution of galaxies. Neutral hydrogen, HI, can be detected across vast distances through the 21-centimeter emission line, a specialized radio signal produced by the spin-flip transition of the hydrogen electron. Because this radiation can penetrate dense clouds of cosmic dust that obscure visible light, radio astronomers use the HI line to visualize the spiral arms of the Milky Way and to measure the rotation curves of distant galaxies. This mapping has revealed that hydrogen is not uniformly distributed, but exists in complex phases, ranging from cold, dense molecular clouds where new stars are born to hot, ionized H2 regions surrounding massive young stars. The presence of these ionized regions, such as the Orion Nebula, serves as a beacon of active stellar formation, demonstrating the ongoing cycle of hydrogen being recycled from the interstellar medium into the stellar interior and then ejected back into space through stellar winds and supernova explosions. Within the architecture of planetary systems, hydrogen dictates the distinction between terrestrial and Jovian worlds. During the formation of the solar system, the temperature gradient of the protoplanetary disk established a frost line, beyond which volatile compounds like water, ammonia, and methane could exist in solid form. Beyond this boundary, the nascent gas giants, Jupiter and Saturn, were able to accumulate massive amounts of hydrogen and helium from the surrounding disk before the solar wind cleared the remaining gas. This resulted in planets that are essentially failed stars, composed primarily of hydrogen. In the extreme interior of Jupiter, the pressure reaches levels exceeding 2 million atmospheres, forcing hydrogen into a liquid, metallic state. In this phase, the hydrogen atoms are so closely packed that their electrons become delocalized, allowing the material to conduct electricity like a metal. This liquid metallic hydrogen is the source of Jupiter's immense magnetic field, demonstrating that even the simplest element can exhibit complex and extraordinary physical properties when subjected to the pressures of a giant planet's core. The role of hydrogen in the deep time of the universe is further complicated by its eventual depletion. While it is the most abundant element, it is also a finite resource on the cosmic scale. As successive generations of stars convert hydrogen into heavier elements through nucleosynthesis, the total amount of available fuel in the interstellar medium is gradually decreasing. This process, known as galactic chemical evolution, suggests that the universe is currently in its stelliferous era, a multi-trillion-year window where the presence of hydrogen allows for the existence of stars and the maintenance of habitable environments. Eventually, the supply of primordial hydrogen will be exhausted, leading to a universe populated by stellar remnants, white dwarfs, neutron stars, and black holes. However, because the half-life of a proton is exceptionally long, potentially exceeding 10 to the 34th power years, the hydrogen nucleus remains the most stable and enduring component of baryonic matter, a permanent witness to the history of the cosmos. The scientific analysis of the 21-centimeter line also allows researchers to peer back into the epoch of reionization, the period when the first stars and quasars began to flood the universe with ultraviolet radiation. This radiation stripped the electrons from the neutral hydrogen filling the void, creating a transparent, ionized interstellar medium. By observing the redshifted signals of this transition, cosmologists can determine the exact timing and geometry of the first light in the universe. Hydrogen is therefore the primary instrument of historical cosmology, providing the medium through which we can observe the transition from a dark, chaotic infancy to a structured and illuminated maturity. The element acts as a universal clock and a physical archive, recording the fluctuations of the Big Bang and the subsequent development of the cosmic web. Furthermore, the abundance of hydrogen in the early universe had a direct impact on the formation of the first molecular structures. While the high-energy environment initially prevented chemical bonding, the eventual formation of the helium hydride ion, HEH plus HEH plus, and molecular hydrogen, H2H2, provided the necessary cooling mechanisms for gas clouds to collapse into stars. Molecular hydrogen acts as a heat sink, allowing gas clouds to radiate away their gravitational energy and reach the densities required for fusion. Without the specific vibrational and rotational modes of the hydrogen molecule, the first stars would have been much more difficult to form, potentially delaying the evolution of the universe by billions of years. Hydrogen is not just the fuel of the stars. It is the cooling agent that makes their existence possible, serving as the essential catalyst for the emergence of complexity in a cooling cosmos. The deep time perspective of element 1 also encompasses the eventual fate of the solar system. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core, leading to a catastrophic structural realignment. As the core contracts and the outer layers expand, the Sun will transition into a red giant, potentially consuming the inner planets. During this phase, the hydrogen burning will move to a shell surrounding the helium core, a final attempt to maintain hydrostatic equilibrium. Once this shell is also exhausted, the Sun will shed its outer hydrogen-rich layers into space, forming a planetary nebula and leaving behind a dense white dwarf. This process will return a significant portion of the solar hydrogen back to the interstellar medium, where it may eventually contribute to the formation of a new generation of stars and planets. This is the ultimate cycle of stellar recycling, a process of eternal return where the first element continues to circulate through the galaxy, facilitating the birth and death of worlds. The sheer scale of hydrogen's influence on the universe is a testament to the power of the simple. A single proton and a single electron, multiplied by the vastness of the cosmos, have created the stars, the galaxies, and the foundational chemistry of life. The hydrogen atoms currently in the human body were once part of the primordial gas clouds of the Dark Ages and the internal furnaces of ancient suns. They have survived the death of stars and the formation of the Earth, maintaining their fundamental identity through trillions of years of cosmic change. Hydrogen is the alpha and the omega of the material world, the substance that initiated the timeline of matter and the substance that will likely be the last to remain. It is the architect of light and the cradle of complexity, an element that has mastered the transformation of emptiness into a vibrant and energetic universe. As the narrative of Element 1 transitions from the cosmic scale to the terrestrial one, the focus shifts to the historical discovery of this inflammable air and the realization of its role in the composition of the most essential substance on Earth: water. The following blocks will explore how the human species moved from a state of total ignorance regarding the nature of the atmosphere to the precise manipulation of the hydrogen bond, revealing the historical drama and the hidden mechanisms that have allowed us to utilize the first element as a source of energy and food. Hydrogen remains the universal constant, a material that carries the signature of the Big Bang into every aspect of our modern lives, from the fuel in our rockets to the structure of our DNA. It is the beginning of everything, and its mastery represents the ultimate achievement of human intelligence in a universe built of protons. The formal identification of hydrogen as a discrete chemical entity occurred in 1766 through the experimental rigor of the British natural philosopher Henry Cavendish, a development that marked a terminal shift from the remnants of alchemical thought toward the empirical foundations of modern chemistry. Before this period, the various airs produced by chemical reactions were often conflated or poorly understood within the framework of the phlogiston theory. Cavendish observed that the interaction of certain metals, such as zinc, iron, and tin, with diluted acids resulted in the liberation of a highly specific gas, which he initially designated as inflammable air. His measurements revealed that this substance was approximately 11 times lighter than common atmospheric air, a physical property that would later enable the first era of human flight. However, the most profound discovery made by Cavendish occurred in 1781, when he demonstrated that the combustion of this inflammable air in the presence of dephlogisticated air, now known as oxygen, resulted in the formation of pure water. This observation was intellectually explosive, as it dismantled the Aristotelian concept of water as one of the four fundamental and indivisible elements. The realization that water was a chemical compound, a product of the union of two distinct gases, redefined the human understanding of the material world and provided the first glimpse into the transformative potential of the hydrogen-oxygen bond. The intellectual successor to Cavendish's discovery was the French chemist Antoine Lavoisier, who recognized the broader implications of these experiments and provided the element with its modern designation. In 1783, Lavoisier reproduced Cavendish's results on a grander scale, proving that water was not an element, but a combination of two gases in specific proportions. He coined the term hydrogen, derived from the Greek words hydro, meaning water, and genes, meaning creator or former. This nomenclature established hydrogen as the water former, a title that reflects its primary terrestrial role. Lavoisier's work integrated hydrogen into the new oxygen-centered chemistry, allowing for the systematic categorization of chemical reactions and the eventual development of the periodic table. The discovery of hydrogen's role in the composition of water also opened the possibility of utilizing the element for large-scale energy storage and transport, a concept that would capture the imagination of the subsequent century. The 19th century witnessed the first practical application of hydrogen's extreme buoyancy through the development of aerostatics. The low density of hydrogen gas made it the ideal lifting agent for balloons and dirigibles, allowing humans to transcend the limitations of terrestrial movement. In 1783, the French scientist Jacques Charles launched the first hydrogen-filled balloon from the Champ de Mars in Paris, demonstrating that a captive volume of element 1 could overcome the force of gravity and carry a payload into the upper atmosphere. This initiated a century of hydrogen fever, where the element was seen as the key to a new era of global connectivity. The grandeur of this period culminated in the construction of massive airships, which utilized millions of cubic feet of hydrogen to lift passengers and cargo across continents. While the inherent flammability of the gas posed a constant engineering challenge, the strategic utility of hydrogen for reconnaissance and transportation ensured its central role in the technological aspirations of the Victorian era. Amidst this period of aeronautical experimentation, the speculative literature of the late 19th century anticipated the eventual transition toward a hydrogen-based energy economy. In his 1874 novel, The Mysterious Island, Jules Verne provided a remarkably accurate scientific prediction regarding the future of the element. He posited that the water currently used to quench fire would eventually be decomposed into its constituent elements, hydrogen and oxygen, and utilized as a source of inexhaustible light and heat. Verne correctly identified that the energy contained within the chemical bonds of water represented a reservoir of power far greater than the coal reserves of the era. This vision of water as the coal of the future was a recognition of the thermodynamic cycle where hydrogen could be extracted, utilized for energy, and then returned to the form of water, creating a closed-loop system of power generation. This prophetic insight remained a theoretical curiosity for decades, awaiting the industrial capacity to manipulate the hydrogen atom at the molecular scale. The most significant and transformative intervention in the global hydrogen cycle occurred in the early 20th century through the development of the Haber-Bosch process. By the late 1890s, the human population faced an existential threat known as the nitrogen crisis. The natural supply of fixed nitrogen required for agriculture was being depleted, and prominent scientists like Sir William Crookes warned of global starvation unless a method could be found to synthesize fertilizers from atmospheric nitrogen. The primary obstacle was the triple covalent bond of the nitrogen molecule, which is exceptionally stable and resistant to chemical intervention. The solution, developed by the German chemist Fritz Haber and scaled for industrial production by the engineer Carl Bosch, required the massive use of hydrogen as a chemical crowbar. The process involves the reaction of atmospheric nitrogen with hydrogen gas under extreme pressures of 200 atmospheres and temperatures of 500 degrees Celsius in the presence of an iron catalyst to produce ammonia, NH3. This industrial synthesis represented the first time that the first element was utilized to bypass a fundamental limit of the natural world. The hydrogen used in this process was derived from the cracking of hydrocarbons, or the gasification of coal, providing the necessary energetic input to break the nitrogen bonds and create the nitrates required for global food production. The impact of this technology was immediate and staggering. It effectively unlocked the Earth's agricultural potential allowing the human population to expand from approximately 1.6 billion in 1900 to the 8 billion observed today. It is estimated that nearly half of the nitrogen atoms currently residing in the human body were fixed through the Haber-Bosch process, making hydrogen the invisible architect of the modern demographic explosion. This application earned both Haber and Bosch Nobel Prizes, yet it also carried a darker strategic weight. The same ammonia produced for fertilizer was immediately repurposed for the manufacture of nitric acid, the essential component of modern high explosives. Hydrogen thus became the dual agent of human survival and human destruction, fueling both the Green Revolution and the catastrophic conflicts of the 20th century. The technical mastery required to manage hydrogen on an industrial scale necessitated the development of entirely new fields of metallurgy and high-pressure engineering. Because the hydrogen molecule is so small and mobile, it possesses the ability to permeate the crystalline structure of steel, leading to a phenomenon known as hydrogen embrittlement. In early Haber-Bosch reactors, the high-pressure hydrogen would penetrate the reactor walls, reacting with the carbon in the steel to form methane gas, which created internal voids and caused the heavy vessels to explode without warning. This forced Carl Bosch to develop a composite reactor design, utilizing a soft iron inner liner that allowed the hydrogen to pass through harmlessly, while a high-strength steel outer shell provided the necessary structural support. This engineering triumph was the first large-scale demonstration of our ability to contain the most elusive element in the universe, establishing the safety protocols that continue to govern the modern hydrogen industry. The historical trajectory of hydrogen also intersects with the development of the first liquid propulsion systems that initiated the space age. The high specific impulse of the hydrogen-oxygen reaction made it the ultimate objective for rocket scientists like Konstantin Tsiolkovsky and Robert Goddard. Because the combustion of hydrogen releases the greatest amount of energy per unit of mass of any chemical fuel, it is the only viable propellant for lifting massive payloads out of the Earth's gravitational well. The engineering of liquid hydrogen storage tanks, which must maintain the element at temperatures below 20 Kelvin, represented the pinnacle of 20th century cryogenic science. The successful utilization of liquid hydrogen in the second and third stages of the Saturn V rocket was the primary reason for the success of the Apollo moon landings, proving that the element discovered by Cavendish in a small laboratory was the only material capable of carrying the human species to another celestial body. The grandeur of hydrogen's history is found in its role as a universal constant that has been periodically rediscovered and repurposed to solve the most pressing challenges of each era. We have moved from a species that viewed inflammable air as a laboratory curiosity to a species that utilizes hydrogen to maintain the global food supply and to reach the lunar surface. Throughout these transitions, the element has remained a reliable and uncompromising participant in the laws of thermodynamics. It is the material that turned the fixed world of the 18th century into the fluid and high-energy world of the present. The historical drama of hydrogen is a record of human intelligence expanding into the microscopic and the macroscopic, identifying the element that connects the composition of a water drop to the energy of a star. Furthermore, the study of hydrogen's history reveals a pattern of increasing molecular control. We have moved from the crude combustion of Cavendish's era to the precise electrochemical manipulation found in modern fuel cells. The element that was once synonymous with the Hindenburg disaster is now being refined into the primary carrier for a carbon-neutral future. This historical evolution is a testament to the fact that our relationship with the periodic table is not static. As our understanding of physics matures, our ability to harness the power of element 1 becomes more sophisticated and secure. We are currently standing at the threshold of the hydrogen age, a period where the predictions of Jules Verne and the industrial capacity of the Haber-Bosch process will converge to create a global energy system based on the most abundant and elementary atom in the cosmos. In the final analysis, the historical narrative of hydrogen is the narrative of humanity coming to terms with the fundamental energy of the Big Bang. Every step in its discovery and application has been a step toward a deeper integration with the primary material of the universe. The hydrogen used in the first balloons, the first fertilizers, and the first rockets is the same hydrogen that formed in the first minutes of time. We are the first species to recognize this continuity and to attempt to harness it for our own survival. This historical aspect of Element 1 demonstrates that we are not merely inhabitants of the Earth. We are participants in a cosmic chemical history that began billions of years before our birth. Hydrogen is the first element, the first fuel, and the first witness to the history of everything. And its journey through human hands is only beginning to reach its full technological and existential potential. The following blocks will explore the hidden mechanisms of hydrogen bonds in the structure of life and the future of fusion energy, showing that the water former of Lavoisier is also the savior of our modern world. The functional integration of hydrogen into the structural and metabolic frameworks of biological life is mediated by the subtle yet ubiquitous force of the hydrogen bond, a dipole-dipole interaction that serves as the invisible architect of molecular complexity. Unlike the robust covalent bonds that form the primary skeleton of organic molecules, the hydrogen bond is characterized by a lower energetic threshold, typically ranging from 5 to 30 kilojoules per mole. This specific energy range is critical for the maintenance of the genetic code. Within the double helix of deoxyribonucleic acid, DNA, hydrogen bonds connect the complementary nitrogenous bases, adenine with thymine via 2 bonds, and cytosine with guanine via 3. This arrangement provides a state of dynamic stability, where the 2 strands are held together with sufficient force to preserve the integrity of the genome against thermal fluctuations, yet remain susceptible to being unzipped by specialized enzymes such as helicase during the processes of replication and transcription. Hydrogen acts as the molecular zipper of life, allowing the digital information encoded in the sequence of base pairs to be accessed and copied with high fidelity. The very possibility of biological inheritance and cellular division is thus predicated on the electrostatic attraction between a partially positive hydrogen atom and the lone pair of electrons on a neighboring nitrogen or oxygen atom. This same intermolecular force dictates the anomalous physical properties of liquid water, which remains the essential solvent for all known biochemical reactions. In a water molecule, the high electronegativity of the oxygen atom pulls the shared electrons away from the hydrogen nuclei, leaving the protons partially exposed. This results in a permanent dipole, where the hydrogen end of the molecule carries a partial positive charge. These charges facilitate a network of hydrogen bonds that create a high level of internal cohesion, leading to water's exceptionally high surface tension, its high specific heat capacity, and its unique density profile where the solid phase, ice, is less dense than the liquid phase. Without this specific hydrogen-mediated geometry, the Earth's oceans would evaporate at significantly lower temperatures, and aquatic life would be impossible as lakes and seas would freeze from the bottom up, crushing the biosphere. The stability of the global climate and the fluidity of cellular cytoplasm are both macro-scale consequences of the microscopic behavior of Element 1. The technological mastery of hydrogen's chemical potential is most elegantly realized in the development of the proton exchange membrane, PEM, fuel cell, a device that facilitates the direct conversion of chemical energy into electrical energy without the thermodynamic limitations of the Carnot cycle. In a fuel cell, hydrogen gas is introduced at the anode, where a catalyst, typically composed of platinum nanoparticles, facilitates the dissociation of the diatomic H2H2 molecule into individual protons and electrons. The PEM serves as a selective barrier, allowing the positively charged protons to migrate through the polymer matrix while forcing the electrons to travel through an external circuit, generating a flow of electricity. At the cathode, the protons and electrons recombine in the presence of atmospheric oxygen to form water vapor as the sole chemical byproduct. This process represents the pinnacle of clean energy engineering, offering an efficiency rate that can exceed 60%, nearly double that of a standard internal combustion engine. The reliability and energy density of hydrogen fuel cells were first demonstrated during the Apollo lunar missions, where they served as the primary power source for the command and service module. For the duration of the lunar transit, the fuel cells provided the necessary electricity for life support, navigation, and communications, while simultaneously producing high-purity distilled water for the astronauts to consume. This closed-loop system is a masterpiece of material efficiency. The fuel that propels the mission also provides the hydration for the crew, effectively utilizing every atom of the hydrogen payload. In the contemporary context, this technology is being scaled for the decarbonization of heavy transport, including maritime shipping and long-haul trucking, where the weight and charging limitations of lithium-ion batteries render them impractical. Hydrogen is the only zero-emission fuel capable of providing the sustained power required for the global logistics network, functioning as a high-density carrier for renewable energy. The ultimate frontier of hydrogen utilization is the pursuit of controlled nuclear fusion, a process intended to replicate the stellar nucleosynthesis occurring within the solar core. The International Thermonuclear Experimental Reactor, ITER, currently under construction in Saint-Paul-les-Douros, France, represents the most ambitious scientific collaboration in human history, designed to harness the energy of the Sun on Earth. The reaction utilizes two heavy isotopes of hydrogen, deuterium, which contains 1 proton and 1 neutron, and tritium, which contains 1 proton and 2 neutrons. Deuterium is an abundant resource that can be extracted from seawater, with 1 cubic meter of water containing enough deuterium to provide the energy equivalent of hundreds of tons of coal. Tritium, being radioactive and rare, is synthesized within the reactor itself through the bombardment of lithium blankets with neutrons. The physical challenge of fusion involves overcoming the Coulomb barrier, the powerful electrostatic repulsion between the positively charged hydrogen nuclei. To achieve this, the deuterium-tritium fuel must be heated to a state of plasma at temperatures exceeding 150 million degrees Celsius, 10 times hotter than the center of the Sun. At these temperatures, no solid material can contain the fuel. Instead, the plasma is confined within a magnetic bottle known as a tokamak. Using massive superconducting magnets cooled by liquid helium to near absolute zero, the plasma is suspended in a vacuum, preventing it from touching the reactor walls. The objective of ITER is to achieve a fusion gain, Q, of at least 10, meaning the system will produce 10 times more energy than is required to maintain the plasma. Successful fusion would provide humanity with a virtually limitless, carbon-free energy source that produces no long-lived radioactive waste, effectively solving the global energy crisis by mastering the primary nuclear reaction of the universe. The development of the hydrogen economy also requires the advancement of high-pressure and cryogenic storage solutions to manage the element's low volumetric energy density. Because hydrogen is the lightest gas, it must be either compressed to pressures of up to 700 bar in carbon fiber reinforced tanks or liquefied at temperatures below 20 Kelvin to be transported efficiently. The engineering of these storage systems involves the study of materials at the limits of structural integrity, as the hydrogen molecule's ability to permeate metal lattices can lead to embrittlement and catastrophic failure. The transition to a hydrogen society necessitates a global infrastructure of pipelines, liquefaction plants, and refueling stations, a multi-trillion-dollar undertaking that mirrors the development of the oil and gas infrastructure in the 20th century. Hydrogen is the master key to energy storage, capable of capturing the intermittent output of wind and solar farms and converting it into a stable, transportable fuel that can be used across all sectors of the economy. Within the realm of industrial chemistry, hydrogen remains the essential reagent for the desulfurization of petroleum products, a process known as hydrotreating. By reacting crude oil with hydrogen at high pressures, refineries can remove sulfur impurities that would otherwise cause acid rain and damage vehicle engines. This application highlights hydrogen's role as the cleansing agent of the industrial world, a material that improves the quality and environmental safety of existing fuels, even as we transition toward its direct use as a primary energy source. Furthermore, the burgeoning industry of green steel utilizes hydrogen as a reducing agent in the production of iron, replacing carbon-intensive coking coal. In this process, the hydrogen reacts with the oxygen in the iron ore to produce pure iron and water vapor, potentially eliminating up to 7% of global carbon dioxide emissions. Hydrogen is the essential chemical tool for the transformation of heavy industry, providing a pathway to material production that is fundamentally compatible with the Earth's ecological limits. The biological and technological narratives of hydrogen converge in the study of extremophiles, microorganisms that thrive in high-temperature, high-pressure environments, such as deep-sea hydrothermal vents. These organisms utilize hydrogen gas, released by the interaction of seawater with hot mantle rocks, as their primary source of metabolic energy through a process known as hydrogenotrophy. This reveals that the most primitive forms of life on Earth are directly powered by the same first element that fuels the stars and our modern rockets. The existence of these hydrogen-based ecosystems suggests that life may exist on other icy moons in the solar system, such as Europa or Enceladus, where internal heating may drive similar geochemical reactions. Hydrogen is the universal signature of habitability, a material that provides the necessary energetic gradient for life to emerge in the absence of sunlight. The hidden mechanisms of element 1 in our lives are thus characterized by a profound versatility that spans the microscopic and the macroscopic. It is the atom that stabilizes the genetic code, the molecule that dictates the properties of water, and the fuel that enables both the exploration of space and the generation of limitless energy. We have moved from a species that was unaware of hydrogen's existence to a species that is beginning to direct its nuclear potential. The transition to a hydrogen-centered civilization is the logical conclusion of our scientific development, as it represents a return to the primary energy and matter of the Big Bang. Every hydrogen bond in our bodies and every fuel cell in our machines is a testament to the fact that the simplest element is the most indispensable catalyst for complexity. Ultimately, the mastery of hydrogen represents the ultimate test of human engineering. It requires us to manage the most volatile of gases, to sustain the most extreme temperatures in the solar system, and to build an infrastructure that mirrors the atomic logic of the universe. The hydrogen in our DNA and the hydrogen in our future reactors are the same protons that formed in the first minutes of time, now being harnessed to ensure the survival of the species. Element 1 is the silent driver of the world, an element that has spent billions of years preparing the cosmos for our arrival, and which now provides the means for our continued progress. The final block will examine the existential trajectory of hydrogen, following these atoms through the terminal stages of the universe and considering the ultimate fate of a world built upon the first element. Hydrogen is the beginning, the middle, and the end of the material story, a substance that will remain the primary constituent of the cosmos as long as time itself continues to unfold. Its story is our story, written in the language of protons and electrons, and its final chapter is yet to be determined by our ability to safely wield its forbidden flame. The ultimate trajectory of the universe is a narrative written in the gradual depletion of its most fundamental resource, a process of cosmic entropy where the primordial reservoir of neutral hydrogen is slowly but inevitably transformed into the inert ash of stellar evolution. This transition marks the boundary between the stelliferous era, defined by the vibrant light of active fusion, and the cold, dark epochs that lie in the distant future. Currently, the cosmos exists in a state of high energy complexity because of the abundance of element 1, which serves as the primary fuel for every main sequence star in the billions of observable galaxies. However, this fuel is finite. As stars convert hydrogen into helium, and subsequent generations of massive stars forge even heavier elements, the total concentration of available hydrogen in the interstellar medium is decreasing. This process of galactic chemical enrichment is a one-way street. Once hydrogen is fused into heavier nuclei, it cannot be returned to its primordial state through any known natural process. The universe is essentially an engine that is slowly consuming its own structural foundation, moving toward a state of thermodynamic equilibrium where the hydrogen batteries of the galaxies will finally be exhausted. The timeline for this terminal exhaustion is measured in trillions of years, a scale of deep time that renders the entire history of human civilization as a negligible statistical flicker. Astronomers estimate that in approximately 100 trillion years, the last generation of red dwarf stars will exhaust their internal hydrogen supplies and fade into white dwarfs. Without the influx of fresh hydrogen gas from the intergalactic medium to trigger new star formation, the galaxies will gradually darken, entering the degenerate era. In this period, the universe will be populated not by the brilliant light of hydrogen fusion, but by the cold remnants of dead suns, neutron stars, and black holes. The vast clouds of hydrogen that once served as stellar nurseries will have been either consumed or dispersed into the expanding void, leaving behind a cosmos that is fundamentally less energetic and less capable of supporting the conditions for life. Hydrogen is the absolute limit of cosmic potential. Its presence enables the existence of warmth, light, and complexity, while its absence dictates the eventual descent into eternal winter. The existential finality of hydrogen is also explored through the lens of theoretical physics, specifically regarding the stability of the proton itself. In the standard model of particle physics, the proton is considered a stable particle with an infinite lifespan. If this holds true, then even after the last stars have faded and the black holes have evaporated through Hawking radiation, the universe will consist of a thin, cold gas of lonely protons and electrons, the fundamental constituents of the hydrogen atom, drifting through an infinite and expanding darkness. In this scenario, hydrogen is the omega of the material world, the final surviving form of baryonic matter that persists long after every other structure has disintegrated. However, certain grand unified theories, GUTs, suggest that the proton may eventually succumb to decay over incomprehensible timescales, perhaps exceeding 10 to the 34th power, 10 to the 34th power years. If the proton is indeed unstable, the hydrogen atom will eventually vanish, decaying into lighter subatomic particles and photons. This would represent the total erasure of the material universe, a point where the first element finally surrenders its existence to the vacuum, marking the absolute end of the history of matter. Until that distant horizon is reached, hydrogen remains the primary anchor of reality and the ultimate repository of universal energy. We are currently living in the golden age of hydrogen, a period where its abundance allows for the existence of planetary systems and the chemical complexity required for consciousness. The realization that every human being is composed of 90% hydrogen atoms by count provides a profound sense of cosmic continuity. We are not separate from the universe. We are a temporary arrangement of its primary material, a localized concentration of Big Bang debris that has developed the capacity to analyze its own atomic structure. Our thoughts, our history, and our technological achievements are all manifestations of the energy stored within the hydrogen bond and the hydrogen nucleus. We are complex hydrogen, looking back at the simple hydrogen of the stars. and recognizing our shared origin. The potential for a hydrogen-centered future on Earth serves as a microcosm of this cosmic narrative. As we struggle with the environmental consequences of fossil fuel consumption, the transition to a hydrogen economy offers a pathway to a sustainable civilization that operates in harmony with the fundamental chemistry of the universe. By mastering the extraction of hydrogen from water and the containment of its fusion potential, we are attempting to replicate the stellar processes that have governed the cosmos for billions of years. This technological pivot represents the ultimate maturity of the human species, moving from the consumption of ancient biological remains to the utilization of the primary element of the Big Bang. Hydrogen is the key to our survival, providing a zero-carbon fuel and a virtually limitless source of power that can sustain our species as we expand beyond the confines of the Earth. The philosophical and scientific importance of Element 1 lies in its role as a universal constant. It is the only element that spans the entire history of time, from the first microseconds of the Big Bang to the final, cold expansion of the distant future. It has seen the formation of the first galaxies, the rise of the first life forms, and the development of the first civilizations. It is a material that does not adapt and does not change its fundamental identity. A proton is a proton, whether it is located in the core of a distant quasar or in the water molecule of a human tear. This stability is what allowed the universe to develop the complexity we observe today. Hydrogen is the silent witness to every event in the history of the cosmos. A substance that provides the structural and energetic backdrop for everything that has ever existed or will ever exist. In the final analysis, the story of hydrogen is a story of total integration. We cannot understand the origins of the universe, the mechanics of the stars, the properties of water, or the structure of our own DNA without understanding the behavior of the hydrogen atom. It is the first in every sense of the word, the first to form, the first on the periodic table, and the first requirement for life. Its simplicity is its greatest strength, allowing it to function as the most versatile building block in the material catalogue. As we continue to probe the limits of our knowledge through particle accelerators and space telescopes, we are constantly encountering the signature of hydrogen, a material that continues to define the boundaries of our reality. The video concludes with a recognition of their subjective finality. The hydrogen atoms currently circulating in your bloodstream and the hydrogen atoms currently fusing in the center of the Sun are part of the same ancient and eternal cycle. They are the survivors of the early universe and the architects of the future. We are merely temporary participants in this multi-billion-year journey, brief concentrations of protons and electrons that have learned to wonder about their own origins. Hydrogen is the beginning, the middle, and the end of the material story, a substance that initiated the timeline of matter and which will remain the primary constituent of the cosmos as long as time itself continues to unfold. It is the Alpha and Omega, the first and the last, the element that built the world and the element that holds the key to its salvation. Through trillions of years of expansion and the eventual decay of the stars, these individual protons will remain, drifting through an infinite void as the final, coherent remnants of a once vibrant universe. They will be the last things to reflect the dying light of the last stars, a material that outlasts every empire, every memory, and every star. This is the ultimate fate of Element 1, to be the foundational material of the Big Bang and the final witness to the history of the cosmos. A substance that turned the emptiness of the void into a universe of light and life. Hydrogen remains the universal anchor, the silent dictator of the laws of physics, and the primary fuel of existence. An element that was always first, and which will likely be the only thing left at the end of time. This is the beginning of everything, a narrative that starts and ends with the simplest atom, the most powerful gas, and the most essential component of our reality. Hydrogen is the eternal mediator of the cosmos, and we are its brief and fortunate messengers.